So now that we've derived this, what I want to do is go by hand and actually develop a feedback control loop that we could do. You've done some exercises earlier with 1D first order system. X dot was equal to, was it 5 minus x brackets squared, that kind of stuff. This appears a lot in these servo systems. That's why I wanted to practice in homework 1 on first order systems. So let me bring my notes that I have on the stuff. So we're going to drive a loop and then, go look at the issues that might arise. So we're going to do a reaction mill, speed, servo, loop. So with the earlier equations, I'm getting tangled. You were given, we found GS IWS omega dot, and from this we found an omega dot, right? And that really means if you have a controlled time period, so given delta t, the n plus 1 new speed we should have is going to be our current wheel speed. Actually, that's a bad, I'm not big N. Let me use little n's. N plus this that we computed right now at the current time, times delta t. You'd be able to figure this out, right? So we know what the new wheel speed should be at the end of the control time step. So what's the goal? Goal is we have delta wheel speed, which is current wheel speed minus desired wheel speed. So from here, this is actually the desired wheel speed that you would have, right? Because from this servo control is an inner control loop. From the outer control loop that we had on the earlier slide, we would now say, okay, this is the acceleration you should have, so therefore over a controlled time period, this is how much I should be changing it. And this is that. And this is what we want to drive towards 0. Okay? So let's derive a system, but we will also need a differential equation at some point. So the inner loop that will control the wheel speed relates to the wheel motor torque, and we had the motor torque equation, so I'm just going to write that one down. So given the motor torque, S is equal to, we called it IWS, so I'll use that. IWS times omega dot transposed with GS hat plus the wheel speed dot, right? That's the one that we'd have. So, okay, this becomes nothing but a tracking problem, right? Just for a simple first order system. So we need a Lyapunov functions. In terms of what arguments do we have to write our Lyapunov function? What do you think, Gavin? Yeah, this is my control setup. My V function has to be in terms of what? Delta omega. That's the thing we want to drive towards 0, right? You wouldn't just put omega in here because that's going to be it's not positive definite, right? Delta omega should be a positive definite expression. Now we need a positive definite expression, so I'm just going to be really boring. Del omega squared over 2. That makes life easy. Then if we take the derivative, you're going to have del omega I was thinking 2 steps ahead. Del omega dot, which is del omega times omega dot minus omega d dot. Oh, I knew what I was missing. I'm going to throw this constant in there. It'll make my life easier. It's a positive constant. So I can do that. Okay, that's still posit definite. It's like when we had the inertia rate squared or mass times mx dot squared over 2 for kinetic energy. It made the equation of motion stuff easier. Okay, so if we do this, now, as before, I'm going to prescribe a v dot behavior I want and then back solve for what control will make that work. So we're going to say this is simply going to be minus p times del omega squared. Is this v dot negative definite or negative semi-definite? Negative definite, right? Because we only care about del omega. So this is negative definite in terms of del omega. So for first order systems, we get that. Like, great, we don't have to do Mukherjee-Chen or Lassalle's invariance principle. We can stop right there and go, okay, if we can do this, it's going to be asymptotically stabilizing. And in fact, it's radially asymptotic. I mean, it's globally asymptotic stabilizing. So good. So we have del omega here, del omega here. This v dots have to be equal, and you can separate them out. So this leads to delta omega times, let's see, here I have to plug in the equations for the system. So the inertia times wheel speed is equal to us minus this term. So I'll have, all this stuff times this is going to be nothing but us minus IWS omega dot gs hat. So that's this term. Then I have minus IWS omega d, and I factored out del omega. That's those two. And if this is equal to this, I'm going to bring this over to the left-hand side, factor out del omega. So you get your classic feedback term, p times del omega. This whole thing has to be 0. So, Julian, what can be argued now with this equation? How do we solve for motor torque?
Solving for the US.
Yeah, how do we do that?
Oh, well, setting the stuff in parentheses equals 0.
Yeah.
Solving for the US.
In here, it's just a 1D, so you could divide by del omega and say, well, as long as it's not 0, I'm fine. But really, the other argument is this has to be true regardless of my initial tracking errors. I need to be able to achieve this, right? So I cannot count on del omega being 0 to drive it to 0. So that means the other term must always be 0. That's the classic argument. So that's what we have, again. So hopefully this starts to look very familiar. Different algebra, different math, but it's the same logic we apply over and over. And if you do that, if this is 0, then US ends up being, let's see, this goes to the right-hand side, so I will have IWS big omega d. I will have minus P, that should be delta omega. And this goes over to the other side, so that will be plus IWS GS hat omega dot. This, I factored out del omega, so it's going to be P delta omega. Okay, yep. So if I can draw that properly, this boxed equation, that's your motor torque equation for a servo loop. Now, if your outer loop is running at 1 hertz, easy number, pretty typical, how fast do you have to run the servo loop? Why? But you said at least. So if you said at least 1 hertz, you are allowing 1 hertz servo loop.
I mean, my reasoning is that you want your control to be faster than what you're asking for.
Which control? You said you want your control to be faster. Be more specific. There's an outer control and an inner control. So which control do you want to be faster?
The inner one, right?
Are you asking me now? I'm looking for an answer. Who has an answer? Henry.
Yeah, you want the inner one to be faster.
Yeah, but faster, what does that mean? Does it need to update quicker? Do you need to run it at 1,000,000 hertz?
Well,
Could you run it at 2 hertz?
What was the rate of the outer loop again?
I'm updating the outer loop 1 hertz.
Yeah, I'd say at least twice as fast, probably 5 times as fast.
So you're saying at least twice, maybe 5 times as fast. Everybody agree with that? Disib?
Yeah.
So
It should be greater than 1 hertz
why?
because the outer loop will require some input, sorry, some output of the inner loop, and you need to generate that input to the outer loop faster than 6 hertz.
Because it really goes back to the same question here. When we derive this continuous control law, well, not continuous, but here we go. Here we had this one, right, that we derived. That's a motor torque. What's the update rate here? Let's maybe start with the outer loop. What determines how often you need to control this digitally? What do you No, not tracking, huh? Not precision. Well, precision, it will have an impact on the final convergence. Yes, the digital, so that is an influence. Andrew, what do you think? So how would you start? You would just start with 1 hertz and cross your fingers? You can say yes. Most people do that. I do it often. Let's just try it. Spacecraft, I know from history that's 1 hertz should be in a ballpark for how, because we move so slowly. That's fine. But what I just said is really the key. I move so slowly. So we keep talking about update rates, and should it be 1 times faster, 2 times faster, 5 times faster? You know, if you have a sine wave and you want to sample this, how many sample points should you take to identify that it's a sine wave? What do you think? 2 points? 2 points will be enough?
I would say 4 because
So I take 2 points, João. And from that, you're going to tell me, oh, that's definitely a sine wave. Well, then, okay, then more than 2. So how many, you think?
I thought it was at least twice the frequency of the sine wave, so.
Yeah, but that doesn't look like very much, does it?
Yeah.
You could have all kinds of odd behaviors. Or if I take 2 points, depending on whether you put them, 1 here and 1 here, you're just going, well, I think I'm doing this. How do I know it's a sine wave? Abby, what do you think? Okay, so if we do evenly spaced, right, 1, 2, 3, 4, yeah, starts to look, but it also could be this then, all right? There's a famous control person. There's a,
time should be less. You need to worry about the Nyquist of that.
right, the Nyquist sampling frequency. Everybody heard of that before? All right, maybe in years, many years ago, I don't know. But that's basically what it comes down to, right? If you want to do this. And with control, it's the same thing. If I'm controlling something here, I'm just going to go to a new figure. So if I'm doing a feedback control, and let's say this is the attitude motion I want to track. And this is 1 minute, and this is 2 minutes as a time scale, right? So that's 60. I'm not going to draw 60, but there's 30 seconds. This would be 15 seconds. There's 5, 10. So 1, 2, 3, 4, 5. You know, that's the kind of sense that you're doing. If you're doing a 6, you know, so it's usually, you know, Nyquist, the rule of thumb is you want to be about an order of magnitude faster, right, than the fastest frequency that you're trying to identify. Then you're in a warm, fuzzy place, you know, and where you should be, just as a ballpark number. So if you're doing this and you're trying to track this, and now our control will hold the torque piecewise constant. All right? So then we're just doing a constant acceleration for that short time period. If you updated this at this figure once a second, do you think you will track this sine wave with an attitude motion reasonably well? Yeah. I mean, constant torque, that actually means constant acceleration, a constant curvature, and you can prescribe a certain slope. You know, so okay, accelerations are constant, but and then in a simplified way, but that gives you a constant slope. If I had to piece this together in little sections of constant slopes, That's a pretty darn good, that's not bad, right? So this is a sine wave in 120 seconds, and I'm sampling once a second. That's 2 orders of magnitude faster, right? That's pretty good. That's going to give you good convergence. You're worried about final accuracy, discretizations. We're in pretty good shape. Could you use 10 seconds? Let me do a different color for 10, red. What do you think? Gut feeling, I haven't run it. I would expect it to probably work, but the discretization errors, as Ricardo was pointing out, can be quite a bit bigger all of a sudden. You can kind of visually see already, those lines between really don't look straight. They start to have a curvature, so you're going to be a little bit off, but the feedback will help stabilize it and make it robust, but you won't just nicely converge asymptotically as you thought you would, or to a small number. This would definitely have an impact there. And 10 seconds is about an order of magnitude difference, right? So it's really not necessarily what are you controlling, because then the same question now comes in with that inner servo loop. If I'm tracking with the outer loop something that varies over 120 seconds, and I'm using 1 second time steps, I'm really fast. My servo loop might also run at 1 second, because my outer, the bandwidth of my outer loop, the actual performance of how is the system moving, is so slow that the 1 hertz was probably a little bit overkill, but it made me really safe for final convergence, right? So it's a ballpark number. In most cases, you make the inner loop faster because you got the outer loop kind of updating at the required frequency to give you the performance that you're looking for a digital implementation of a continuous system. And then you need the inner one probably to be running quicker to track that, right? And that's the challenge there. So we might have to run quicker. The inner one too, this feedback law that we're looking at now, oh, wait, I have to go back slides here. So we derive this one. If we want to derive that, great, that will, this assumes a completely continuous system, that every time step I'm getting a new, what's my tracking error, that I'm computing this constantly, but really I'm updating this maybe at 1 hertz. So what is going to happen practically is, if you want this kind of a behavior, what will happen is it's actually going to try to converge onto the desired, if this is an omega, rates that you're going to have. And you get this very big stair-stepping effect, which approximates the behavior. You don't get exactly the behaviors you're looking for, so, but you're close enough. So how do you get the stair-stepping to be less? You make much smaller time steps, right? That's why these speed loops need smaller time steps typically than the torque loop. If everything is running at a high frequency, you might be just fine with everything running at the same digital update rate. But again, the argument has to be the update rate digitally versus the bandwidth of the performance. If the fastest thing that you want to track is 2 hertz, you should not be controlling, once a second, because you're just way too slow to keep up with that. Make sense? So think of the combination, digital sampling plus performance has to drive it. So here, if you made now a faster update rate, right, you could get this to kind of start to look a lot more like what you want. Anybody seen a stepper motor work? Some kind of thing that can rotate? How does it sound, Anthony, when you turn on a stepper motor to rotate?
It sounds very herky-jerky.
Yeah, it's like, right? Because it's really it's hitting it hard with a really high gain to go, you want to be at this angle? Whack. Now you want to be at this angle? Whack. And it puts you there. So it's really herky-jerky in how it gets you. But that's kind of how you're driving the wheels then. So now you can play with the gains, right? You could back off on this. You don't want to be quite as aggressive and say, okay, I'm giving you 1/10 of a second to get there. You don't have to get there in a millisecond, right? And so you can try to smooth it out. That's where you would balance with it. The other part is we have a feed-forward term, which is great because it will give us, well, if you're here now and you're supposed to be here later, you're kind of getting the trend. So if you don't have a tracking error, you should be increasing. But that feed-forward term can be difficult if we only discretely update our desired wheel speeds at 1 hertz and we're running this at 10 hertz. You're going to have these things competing. Because if you're running the outer loop at 1 hertz, it's going to say, okay, you're supposed to be 10 RPM faster, right? And this is going to go, great, get me there. But once it gets there, this also says, well, the last one was minus 10, so I am moving at about 10 RPMs per tenth of a second acceleration difference. It's going to feed forward that rate even though you got there, and those two things will start to compete. And that's all due to because you got a digital, this is an inner loop, and we're not updating smoothly. You could try to make an interpolator that you go, well, what's the last? You can get fancier. So 1 second ago, what was mine? What is it now? And instead of then doing a complete difference, you could try to interpolate maybe. I don't think most people do that. So what an actual servo looks like typically is they tend to remove this, and in fact they remove this as well. You make this term big enough to compensate Earth, the spacecraft accelerations tend to be pretty slow. And you just go, that's small. And whatever unmodeled disturbances you have, you will just compensate and put a bigger gain in there, you know. So anyway, but this gives you the stair stepping. So that's why, whereas the torque doesn't just hold that wheel speed constant, it holds the slope constant, the torque. So I can get away with bigger time steps updating my torque loop and still approximate this line versus the wheel loop tends to kind of, like a stepper motor, get you there quickly, and then until you update the outer loop, it gets to the next one and then updates it again, and it gets it there, right? So obviously, any of these servos won't be perfect. They may not give you the torque that you asked for. So how do we get this still to be stable? And the answer is the outer loop, right? The outer loop that you had will update, let's say 1 hertz, and if you aren't at exactly the altitude it thought it would go with all these closed loop dynamics, it just goes, okay, well, we're off by 0.1 degrees. So here's a new torque that'll put us back on track, right? And so that's what kind of, there's an outer loop that's going to keep that inner loop stable and keep it converging. But these two things have to be balanced. You can't just throw in any arbitrary gains. You can't make the inner loop converge in 60 seconds, but the outer loop converges in 1 second. That's not going to work. The outer loop is, its stability is predicated on the assumption, if you do a speed loop, that you actually get these changes in velocity that you're asking for. So if those take way longer than you think in the control bandwidth, you can drive things horribly unstable. You typically want to get the inner loop to converge an order of magnitude quicker. That basically leads to the control separation principle, that we can talk about the stability of inner loop, and then on the outer loop we assume we will have these behaviors that we do. Essentially what we do with torques, when we say, yeah, we just hold it piecewise constant, and that's, close enough. Comes back to Nyquist. Nyquist did a lot of good work. Okay, that was it for the reaction wheel speed loop. Julian.
But like looking at the diagram, it totally made sense what you said, but what am I missing with the times 2?
I don't remember the details of Nyquist stuff there, but it had to do with sampling. But I think it was more than twice.
I think it was because you keep sampling over multiple. Like I think it's 2 n plus 1. And so like over one way you still can't do it, but over one. Oh, okay.
Maybe that's the thing then. Okay, thanks. I should look up Nyquist before I talk about it again. But to me, the rule I remember is if you want to sample something like that and the fastest frequency is 50, I need to be something at least an order of magnitude faster. Then I feel like then it's not going to be a problem. I'm going to get enough points and I will get there, right?